Well, hello and welcome. We are pushing into activity 23 on none other than lesson 23-2, known as the ambiguous case. And so we're going to see that word pop up. So I thought even before we actually dive into the lesson, we'd actually look at the definition of ambiguous. It's an adjective, which means open to more than one interpretation, having a double meaning, unclear or inexact because a choice between alternatives has not been made. So what we're saying is that there are two choices here, and it's unclear which one we're going to choose. So let's put that word into context with what we've been learning by looking at our learning targets. So we're going to understand when the ambiguous case of the law of signs occurs. So in lesson 23-1, we learned that the sine of an angle, actually, let's go and draw a triangle real quick. And it's not necessarily a right triangle. Remember, we're not using necessarily, of course, we can use the law of signs if we need to on a right triangle, but we don't have to. We have other methods to find missing sides of right triangles. We're now learning how to find missing sides of any triangle. So we're learning the law of signs simply says that the sine of an angle over its opposite side is equal to the sine of another angle in the triangle over its opposite side length, and also equal to the sine of the third angle over its opposite side length. And so we used this in the last lesson to find missing sides of other triangles besides right triangles. In fact, if you recall, in the Check Your Understanding, we actually learned how to find the missing side of a right triangle as well. So it works for any triangles. That's the great thing about this law of signs that we're learning. But we're seeing here in our learning target that there is an ambiguous case. There's an opportunity for two answers to be possible. So we're going to have to study that, and we're going to have to understand when to use it, and then solve problems using that ambiguous case of the law of signs. So for the sake of the presentation of this lesson, I'm definitely going to start out these first three items doing it a little bit different, but it is a pretty interesting idea here. Fire spotters at stations located at Q and R notice a fire at location S. So we're still talking about three vertices, so we're dealing with a triangle. And the distance between stations Q and R is 15 kilometers, and the distance between station R and the fire, which is located at vertex S, is 12 kilometers. So we know two distances, and we know that station Q forms a 38-degree angle with station R and the fire. And they ask us to find the distance between station Q and the fire. So item one, they tell you that you can cut straws or coffee stirs that are 15 centimeters, 12 centimeters, just to represent the length of the distances that we had in our problem. And then you can use a protractor to form a 38-degree angle at vertex Q. However, we really haven't taken the time to construct triangles using this method, so I'm going to show you a slightly different idea that's happening here to explain items 1 through 3. And notice they're suggesting how many different triangles can you make using a 38-degree angle and side lengths of 15 centimeters and 12 centimeters. Sketch the triangle. So for starters, we'll have a 38-degree angle. And remember, the measure of an angle, and this is, I believe, located at vertex Q. The measure of this angle Q has nothing to do with the length of this side or this side. Nothing. In fact, an angle, the definition of an angle is when two rays meet or intersect. And so these rays could continue on forever and ever, and it's still a 38-degree angle. So with that in mind, the measures of these other two sides that they give us, 15 kilometers and 12 kilometers, don't actually dictate this angle measure. So it says, let's see, the distance between Q and R is 15. Now, I will say this, if you're wondering how did I get that 38-degree angle, I just sketched it. I knew 45 is half of 90, so that's probably going to be pretty close. So the distance between Q and R is 15, so I'll just keep extending that ray and just say that this is 15 and that R is somewhere right here. Well, then they tell us that S, which is the fire, is 12 kilometers between station R and the fire. So S just simply has to be 12 kilometers from R. Now, here's the issue. We can continue this segment as much as we want. Point S is going to be somewhere on this ray that Q is also on, but it has to be 12 kilometers from R. So this goes back to actually something we learned about triangle congruence, and you'll notice that in item 3. So we could actually draw, and again, I'm just sketching this out. I don't know this for sure, I'm not measuring. We could actually draw, saying this is 12, we could draw a segment like so, such as 12 kilometers or 12 centimeters from R to S. And then we could also actually take that same distance and draw that, let me draw that actually a little bit more convincing. Draw that same length from R to S still on that same ray that Q is on, such that S is now here. So we could actually have, based on these measurements that they gave us, we could have an acute triangle QRS, or we could have an obtuse triangle QRS. And it said, why could you form two different triangles? Well, it's all based on angles and their opposite sides. The measure of angle Q, although it's somewhat dependent on this opposite side, we could extend these rays, especially this ray here, such that S could be in two different locations, and still the distance from R to S is 12 units. This really goes back to what item 3 is talking about. Is there a side-side angle criterion for proving two triangles congruent? And how does this help explain your answer to item 2? So I'm actually going to pull up another tab here, something that we looked at when we explored side-side angle. So right now, when I click that button, you're looking at two triangles that are in fact congruent. Not playing any games with you. So assume that angle A is 38 degrees, angle P is 38 degrees. The distance from A to B is 15, just like the problem was. The distance from P to Q is 15. The distance from B to C is 12, and the distance from QR to 12. The problem here is, and what I just showed on my sketch, is that we can actually move point R along this segment that Q is on, or P is on, excuse me, move this vertex that P is on, move it such that QR is still 12 units or still congruent to BC, but now angle R shows an obtuse angle instead of acute. So here's that ambiguous case. Angle S could be an acute angle, or it could be an obtuse angle. And so we're actually going to use the law of sines in both of those regards to figure out which of the two measures it could be. So for the sake of moving on, there's the ambiguous case. Based on what we have here, we have an angle measure, its opposite side, one other side measure, and not necessarily its opposite angle. So this is when the ambiguous case occurs, because now we could have an obtuse angle opposite of that side, or we could have an acute angle opposite of that side. So we're going to explore that idea here on item 4. So let's start putting it into context. The problem you just explored is an example of the ambiguous case of the law of sines. You know, two side lengths and an angle measure, which is different than what we saw in lesson 23-1. For the most part, we knew two angle measures and a side. So we're going to use the law of sines to complete the equation to find the measure of angle S. We're just going to continue that method that we actually saw in the lesson practice on 23-1. So let's go and pause the video right here. Complete item 4A through B. Make sure you have your graphing calculator handy. And complete 4A through B before moving on. Okay, so just to give you some context here of where this proportion came from, I just drew the two possible triangles. I really just went back and took this sketch and separated it to the two possible triangles. So again, we are noticing that based on the information given, that angle XS could be an acute angle like the drawing we have here, or it could actually be an obtuse angle like the drawing we have here. But regardless, our first task is simple: find the measure of angle S. So the reason they use the sign of Q over Q is we know the measure of angle Q and its opposite side. Regardless if RS has this slope or this slope, the distance from R to S, which is lowercase q, is 12. So that's why they use the sine of q over q equal to, if we're looking for angle S, we probably should use the sine of S over S, which again, we're using that for sure because we know the opposite side of angle S, which is 15. So we replace Q with its angle measure, 38 degrees, replace its opposite side length with 12. Again, we don't know the measure of angle S, so we'll leave sine of S over its opposite side, which is 15. So I want to show that cross multiplication. 15 times the sine of 38, which is 15 times the sine of 38, and 12 times the sine of S. We're going to divide both sides by 12 so that this cancels out or becomes 1, and we're left with sine of S equal to 15 times the sine of 38 over 12. And remember, if the entire goal is to find an angle measure using these trig ratios, we're going to use the inverse trig function. So the sine inverse of this ratio right here is the measure of angle S. So I'm going to show you again how to put that in the calculator. So 15 times the sine of 38 over 12. So we're going to, of course, use the inverse sine. I'm going to use an extra set of parentheses, especially for those using the TI-83. 15 times the sine of 38. So 15 times the sine of 38. We'll close parentheses there and divide that by, just making sure I put it in correctly, 12. And it gives us 50.3. And we'll just assume we're rounding to the 10th here. Let's see if it actually tells us to. Oh, it says round to the nearest degree. So 50.3, that 3 tells that 0 to stay where it is. So we're going to say that angle S is approximately 50 degrees. Now, again, we're exploring this ambiguous case that there's two possibilities. So right now, we have just established that the measure of angle S for the acute triangle, because we did find an acute angle, this angle is 50 degrees. So that would mean that we could actually find angle R. But again, what we're really stressing here is that there is another possibility for angle S being an obtuse triangle. So let's press on to see how to find that measure. So we're actually going to chunk item 5 with itself. There's a couple parts to it. So pause the video, try to digest it, read it, see what it's telling us, and try to complete items A through C before playing through. So we know there are two possibilities for angle S. We just found one could be 50 degrees, and so we're going to explore what the other possibility for angle S is. And that's what this text is telling us. So there are two angles between 0 and 180 degrees whose sine is 0.766, one acute and one obtuse. And think about what we're exploring here, one acute, one obtuse. In fact, both of those, the sine of the angle whose sine is 0.766 is the angle 50 degrees. So the acute angle sine of 50 degrees is 0.766. The obtuse angle actually uses the 50 degrees as a reference angle. So we're going to take 180, subtract the 50 degree angle, and we find that the other possibility for the obtuse angle is 130 degrees because the sine of 130 and the sine of 50 are the same thing. And I actually showed that here. So it is easy just to breeze past this and just say, okay, cool. If we know one angle measure, we subtract it from 180 and we find the other possible angle measure. But I want to explain as we get further in the trig, especially for those moving on into higher mathematics, why that's so. So let's go back to the coordinate plane here. Let's assume that on the x-axis to the right, this is 0 degrees. And as we rotate counterclockwise, we get all the way to 180 degrees. So if we start at 0 and go up and we stop here, we create a 50 degree angle. And so the relationship of the sine of 50 opposite of that angle to its hypotenuse, when you compare these two measures, the side opposite of that 50 degree angle, and notice I actually suggest that this ray can continue on. So this ray could keep going on forever and ever and ever and ever. If you have this 50 degree angle measure, and look, we're looking at a right triangle, when you compare this opposite side to its hypotenuse, it's actually going to be equal to another angle measure over here. Let's think about that. Now view from 180 going 50 degrees up. So 50 degrees up from that would actually be a total of 130 degrees. So from starting from 0 all the way over here, that would actually be 130 degrees. And so very similar, kind of a reflected idea of what we just said over here. When you compare the opposite side of this angle, which is also a 50-degree angle, because 180 subtract 130, this is also a 50-degree angle. When you compare that opposite side of that angle to the hypotenuse, you're going to get the exact same ratio you did over here. So it makes sense as you start studying this trig more that it's not just limited between 0 and 90. It's actually all the way up to 360 and so forth and so on. So there are two angle measures, or there's another angle measure that actually has the same sign as 50 degrees, and it's the sine of 130. So the other possibility for the measure of angle S is 130 degrees. So now on B, if one possibility, angle S is 50 degrees, and one possibility is 130 degrees, now we can find two possibilities for angle R. So the measure of angle R, if angle S is 50 degrees, angle R is 92 degrees. And if angle S is 130 degrees, angle R is 12 degrees. So I'm actually going to go back and just kind of throw that in there, put that in context. So if angle S is 50 degrees, then angle R is 92. And if angle S is 130 degrees, angle R is 12 degrees. So again, this is the ambiguous case. There are two possibilities or two alternatives based on the information that's given. So on item C, we're actually going to write two equations because we don't know which angle measure S is. And if we don't know which angle measure S is, we don't know what measure of angle R is. And so we're actually going to write two equations to find the two different possible values of QS. Because not only are we changing the possibilities of angle S and angle R, notice there could be two angles there, we're also changing the possibilities of the distance between Q and S. Notice if it was the obtuse angle, QS is pretty narrow, and if it's the acute angle at S, then QS is pretty wide. So we're actually, there's quite a bit of ambiguity. I think that's how you say that, quite a bit of ambiguity based on what we are given. So for starters, the sine of 38 over 12, again, we're using that Q ratio because we actually have the measure of angle Q and its opposite side. So the sine of 38 over 12 is equal to the sine of 50 degrees. Correction, it shouldn't be 50 degrees. That would actually be finding S, so I actually need to go in and change a couple things. So it should actually be 92 and 12 because we're finding lowercase r based on the measure of angle R we just found. So let me go and change a couple of these values here. So get rid of sine of 50. That's a pretty quick fix, fortunately. So let's replace 12 times the sine of 92 here and 92 here. And then, of course, 12 over here and 12 over here. Okay, so now that that's fixed, I forgot that we were finding lowercase r, so we definitely should use angle r, which we just found in item B. So I replaced QS with lowercase r. We've been using the lowercase letters to represent side lengths. So don't get confused there. I just replaced QS with lowercase r. So r times sine of 38 equal to 12 times the sine of 92. Divide both sides by the sine of 38 so that r can be by itself. And we'll put that in the calculator now. So r is equal to 12 times the sine of 92, now that I fixed that, divided by the sine of 38. Twelve times the sine of 92 divided by the sine of 38, which is 19.47, which I believe they told us to round to the nearest tenth. They did. And so that 7 is actually going to round that 4 up to a 5. So the distance is 19.5. I think we're actually in kilometers. So that's one possibility, and that's if QS or if angle R is a 92-degree angle. So look at that. So if angle R is a 92-degree angle, then the distance from Q to S is 19.5 kilometers. So you have to imagine if angle R in this second case is 12 degrees, then the distance from Q to S is going to be a lot shorter than that. Definitely shorter than 19.5. So now let's find that measure. So again, now that I fixed that, we replace QS with lowercase r. So r times the sine of 38 equal to 12 times the sine of 12. Remember, this is 12 degrees from the angle, and this is the opposite side of vertex Q. So just keep those two 12s distinguished. So this is r times the sine of 38. So again, we're going to divide both sides by the sine of 38, and r will equal 12 times the sine of 12 degrees over sine of 38. So we could just simply go back here and just replace the 9 with a 1, because that's the only change. It was 92 now to 12. And the distance for r, which is QS, is 4.1. 4.1 kilometers. Which has to make sense. We should start understanding how sides and angles relate, especially in this scenario. If the angle opposite of QS is a narrow angle, then that side length has to be pretty narrow, which we just found is 4.1. If the angle opposite of this side is pretty wide, in fact, it's larger than a right angle, then that has to be a pretty wide measure. In fact, that's the largest angle in the triangle. 92 degrees is the largest angle in the triangle, so its opposite side has to be the greatest measure, which it just was, 19.5. But now, in this other case, angle S was the largest angle, so the side opposite of it actually had to be the largest measure there. So remember how these sides and angles relate so we can actually make sense of the answers that we get. Even as complex as this work is, we need to make sense of our numbers. So the last thing we're going to do together is complete item 6. And notice they didn't actually give us a triangle, what it looked like, because there are two possibilities here. So complete item 6 before playing through. Okay, since this information can be rather lengthy, especially with the amount of work that we have to do just to find these missing measures, I thought I'd go and play it through here and kind of explain the thought process to find, again, the two possible values. This is the ambiguity, I believe is how you say that word, that the law of sines creates based on the information given. So if we're given triangle ABC with angle B equaling 40 degrees, and notice I just kind of drew some angle like I did initially, 40 degrees, and the length from A to B, so if B's here, A is going to be up here along that same ray, such that A is 12 units from B. So I labeled that 12 units. But then the distance from A to C simply has to be 8 units, regardless of what the measure of angle C is. So the first possibility, I know it's going to create an acute angle as one possibility. So I drew that this distance from A to C is 8, and I didn't know angle C or angle A at the beginning. I should go and point that out because there's actually two possibilities. So for starters, I knew angle B and I knew its opposite side. So I knew I had to use the sine of B over B because I have its angle measure and its opposite side. Well then, if we're trying to find angle C first, and I love that they encourage us to do that based on what's given because we have its opposite side. So we definitely need to find angle C first because we have its opposite side. We definitely couldn't have found angle A first because we didn't know its opposite side. So the sine of B over B is equal to the sine of C over C. So I replace angle B with 40 degrees, lowercase b with 8, and notice I labeled them lowercase a, b, and c. We don't know angle C, but we know its opposite side is 12. So then we use cross multiplication. 12 times the sine of 40 degrees equal to 8 times the sine of C. Divide both sides by 8 so that it's just sine of C equal to 12 times the sine of 40 over 8. And again, if we are finding an angle measure, which we are, we use the inverse trig function. So we're really focusing on the inverse sine function right now because we're using the law of sines. So c is equal to the sine inverse of 12 times the sine of 40 over 8, which I found 75 degrees. So let me just recall how to type that in. So the sine inverse, use extra parentheses just for my TI-83 students, 12 times the sine of 40, close parentheses, divided by 8. And we get 74.6. And I'm going to just use what we did in the last direction, round to the nearest degree. So this 0.6, that tenth, tells the 4 to round up to a 5. So we established that angle C is 75 degrees. But review or recall what we just said back here. There's actually two angles who have the exact same sine. So the sine of 75 degrees is actually equal to the sine of 105 degrees. And just recall how we found that. We just took 180 subtracted from 75 to find this other possible measure for angle C. And so we can prove that if you like. The sine of 75 is actually equal to the sine of 105, 0.9659. So they are in fact equal. So there are two possibilities for angle C, which is 75 degrees or 105 degrees. Now, whatever angle C is going to determine the measure of angle A. So if the measure of angle C is 75 degrees, 180 minus 40 minus 75 is 65 degrees. So the measure of angle A is 65, assuming angle C is 75. And if angle C is 105 degrees, 180 minus 40 minus 105 is 35 degrees. So we actually have these two different sets of angle measures based on the law of sines, hence the term ambiguous. So now we're going to go through the process of finding BC. And recall, if we have angle A being 65 degrees, this distance here is definitely going to be greater than if the measure of angle A is 35 degrees. The distance here is going to be a little bit smaller. So just keep those two separate. So now pause the video and try to find the length of B to C, or lowercase a in this example, using the law of sines. So since there are two cases, for the first case, we are going to go with the measure of angle C being 75 degrees. Therefore, the measure of angle A is 65 degrees. Now, we could use the sine of C over C to find this measure here, BC, which we label lowercase a. But recall that 75 degrees is actually a rounded value. In fact, if you actually look at the answers to the Springboard for item 6, you'll see that they didn't exactly get 75 degrees and 105 degrees. So it is a rounded value. So I'm going to stick with the sine of B over its opposite side because it was given to us. So I chose the sine of B over B equal to, if we're trying to find the segment BC, we're technically finding lowercase a, so the sine of A over A. And again, we're using angle A in this first instance as 65 degrees. So replace angle B with 40 degrees, its opposite side 8. Angle A was 65 degrees, and its opposite side we don't know. Did cross multiplication. Hopefully some of you are getting just the hang of this, writing proportions, cross multiplying, dividing. I know it looks intense. In fact, it just sounds intense, just that we keep saying this word sine, sine, sine all over again. But it's A times the sine of 40 equal to 8 times the sine of 65 degrees. And since this is A times the sine of 40 degrees, we'll divide both sides by the sine of 40 so that this cancels out. So A will equal 8 times the sine of 65 degrees over the sine of 40. I'm just going to show you again when we put that in the calculator. 8 times the sine of 65 degrees over the sine of 40, we get 11.27, which will assume that this 7 rounds that 2 up to a 3. So we'll say the length of the side BC is 11.3. And they didn't give us any units here, so we'll just leave it as that. Or, so think about this before we even find the other possibility for the length of BC. If the measure of angle A is 65 degrees and its opposite side is 11.3. Now, when we find the measure of angle A is 35 degrees, its opposite side, since angle A is definitely smaller than what it was up here, its opposite side has to be smaller than what it was here. So just keep that in mind. Make sense of the numbers as we go through. And if you notice with all this work right here is identical to all the work we did here, with the exception of this angle A, 65 degrees, is now 35 degrees. So to save yourself, if you're really understanding this math, to save yourself, you can just simply go in and change the 65 degree angle to a 35 degree angle. And that makes the math a lot quicker for us. If we just understand really what we're doing here is we're just changing the possibility of angle A between all this work here and all this work here. We're just changing the measure of angle A. Then just simply change the measure of angle A. So 8 times the sine of 35 over the sine of 40 is 7.1, because the 3 tells that 1 to stay where it is. So the other possibility for BC is 7.1, which does make sense, because when angle A is 65 degrees, its opposite side is 11.3. And when angle A is 35 degrees, its opposite side is smaller, 7.1. So I will say this, once you get this work done, if you're understanding that all we're doing is changing the measure of angle A, you don't have to rewrite this work here as long as you understand what we're doing. So that is the end of lesson 23-2. Definitely not simple math. There's no way around it. It's not simple math. So I encourage you to go back to the parts that are a little bit more confusing, parts that you need to watch again, see where I messed up here with replacing those values. So it's very important that we understand where this math comes from, how to use it, and when to use it. So go back and watch any part again that you might need. I'll even go back right here and go and put in 4.1 kilometers just to tidy it up for note's sake. But go back to the learning targets, reevaluate your understanding. As always, complete the practice below, just so we can keep getting better and better at this work. Thank y'all for watching.